Welcome to today's webinar. My name is Martin Berry and I work for Royal Haskoning. I am the chair of the Guild's Intake, Outfalls and Landfalls technical panel. And we're presenting today's webinar for you on behalf of the Guild. And this is around the Arklow wastewater treatment plant's outfall project. This was a project that was entered into the 2023 Subsea project awards and was the winner in that category last year for the Guild Awards. So we're proud to present this one, and our presentation today will be given by Daniel Akpan, who is a design engineer with Royal Haskoning, and Casper Janssen, who works for Van Oord, who are the marine contractor in the project. So I will hand over to those two to give the presentation. We will do questions at the end, so please, if you have any technical questions or observations, please put them in the chat and we will run through those at the end. Presentation should be about half an hour and then we'll do the questions at the end and a bit of a summary. Okay, so I'll hand over to Daniel and Casper, and I hope you enjoy the presentation. Thank you.
Thank you, Martin, and good afternoon, everyone. As Martin said, my name is Daniel Akpan, and I'm a marine pipeline engineer. Been working for Royal Haskoning for the last 8 years, and on this project, I was the project manager for Royal Haskoning, and I was also involved in some of the pipeline design engineering as well. So this slide is just an overview of the main companies or organizations that were involved with the project. Irish Water were the client. Word & Burke were the main contractor responsible for the wastewater treatment plant and revetment works. And Van Oord were subcontracted to Word & Burke to undertake the marine works. Royal Haskoning DHV, we were the Van Oord's designer for the long sea outfall and associated structures. And I'll just quickly move on to the overview just to provide a little background to the project. Arklow is a town on the southeast coast of Ireland. And in Arklow, there were no wastewater treatment facilities. As a result, untreated wastewater was being discharged directly into the Avoca River. This discharge was not compliant with wastewater treatment regulations, and it was also not good for the water quality of the river. And this led to Irish Water proposing the development of a new treatment works and long sea outfall to discharge the treated wastewater and improve the water quality of the river. So on this slide, you can see the location plan where you have the long sea outfall pipeline in blue, and there's also an indication for where the proposed treatment works was going to be. So for this project, the concept design of the long sea outfall was previously was conducted by a previous designer. Royal Haskoning only got involved at the tender design stage where we produced the tender design and subsequently the detailed design for the long sea outfall. The basis of design took into consideration the site conditions and available environmental data for the site location, as well as the specific long sea outfall requirements, which were specified by the client. We used those requirements to develop and finalize the route of the long sea outfall, the hydraulic design, which included diffuser configuration, and then we did the pipeline on bottom stability, scour, and rock armor protection design as well. So on this slide, there is also a snapshot of the main design parameters that we considered during the design of the long sea outfall. So for the detailed design, our DHE scope of work included the review of new information, as the client had conducted some new surveys to aid the detailed design scope. So for example, we had some new Batty survey, which we used to conduct a burial depth and scour assessment. We also conducted the wave modeling for the pipe and revetment works, the hydraulic design update, stability design, and we looked at the details for the landfall and revetment crossing. We also carried out a Cat 3 check of the revetment design that was done by Wood and Burke. So the Longsea Outfall pipeline was a 630 OD SDR17 polyethylene pipe. It was approximately 927 meters long, and the diffuser configuration, which you can see in the figure on the slide, consisted of 6 risers, and each with 4 ports, making a total of 24 diffuser ports. And each port was fitted with a non-return duckbill valve at the end of it. Haskoning also conducted some pipe structural calculations to verify that the SDR17 pipe was sufficient for the design conditions. So this slide shows the route of the new Longsea Outfall. As previously stated, the Longsea Outfall was approximately 927 meters long. We had a St. Patrick's cross that was used to indicate the start of the outfall. And this was then routed underneath the revetment in a trench all the way to the discharge location, which was indicated with a marker buoy. During the routing of the pipeline, we identified an existing pipeline and subsea cable within close proximity to the LSO works. The existing pipeline is shown in orange to the north, and the subsea power cable is on the opposite end in pink. For the subsea power cable, we were already compliant with the applicable exclusion zones and separation distances, so nothing further needed to be done. But you might notice that the existing pipeline actually protruded into the red line boundary for the works. Luckily, we were able to confirm that that pipe had been redundant for many years, and so we didn't have to reroute the LSO as a result of that pipeline. A UXO risk desk study was also undertaken by VO for the site location, especially along the route of the LSO. So as previously mentioned, we conducted some pipe structural calculations for the entire length of the outfall. But this was especially critical for the revetment crossing location, just to ensure that the pipe wall thickness was sufficient to withstand the load that was coming from the revetment. The calculation results did indicate that this SDR17 pipe was sufficient, and we also allowed a 0.7 minimum pipe clearance from the toe of the revetment, as you can see in this slide. So typically at the onshore-offshore interface, and due to tidal fluctuations, there's usually a chance of air being drawn forward into the offshore sections of the pipe. This can affect the hydraulics of the pipe, so we limited the slope of the pipe underneath the revetment, which is based on air transport calculations that we had conducted just to reduce the risk of air being drawn forward into the offshore sections. If you look on the figure on the screen, you will notice that there's also an air valve chamber just before the revetment, which we also included to get rid of any unwanted air in the system. So the hydraulic design was undertaken to confirm that the pipe size was sufficient for the design flows. The pipe was designed to discharge by gravity. at all stages of the tide, including the extreme water level, which was the worst case. The pipeline was also designed to achieve self-cleansing velocities of 0.6 meters per second for minimum and maximum flows. And just due to the diffuser configuration, which had 6 risers and 24 ports, we had to make sure that the flow distribution was as balanced as possible across the entire diffuser configuration. We also had non-return ductile valves on each port, and that was just to prevent backflow into the pipe and to aid dispersion. So the Outfall pipeline was required to achieve absolute on-bottom stability within the trench without relying on any backfill material. We used the StableLine software, which is a DMV-approved software to calculate the required weights for absolute stability in line with the DNV RPF 109 code. The additional weighting that was provided in the form of concrete colors and kennels in the arrangement that you can see on the screen. The concrete colors were fixed at 3.5 meter centers to aid the installation method, which was a floating flood method. The floating flood method is where we put just enough colors on the pipe to allow the pipe float when it's empty and then sink when it's pumped full of water. Then after the pipe is sunk onto the seabed, we then add additional concrete kennels in between those colors, depending on absolute stability requirements. So as mentioned earlier, as part of the scope, we also conducted a burial depth and scour assessment. The reason for this was to determine the risk of seabed erosion and to ensure that the pipeline would remain buried and protected from third-party damage throughout its design life. To achieve this, we reviewed the coastal erosion data for the site location, and we were able to demonstrate that the erosion levels were typical and not excessive, and therefore the 1.5 meter cover that we proposed for the pipe was sufficient to keep the pipe buried and protected without the need for additional scour protection. We also looked at the historical vessel traffic for the site location, and just based on the largest vessel that we identified over a 10-year period, we were able to demonstrate to the client that there was no risk of sort of anchor damage to the pipe from any of the vessels in that location. Around the diffuser area, it was necessary to provide some scour protection. This is just due to the discharge and flows from the ports, because they can cause scour. And as you can see from these figures, we provided some rock armor. We had 2 layers. We had the rock armor layer, and then we had a filter layer at the bottom of that. And that extended over a distance of 68 meters at the discharge location. Also, because the risers protruded above the seabed level, we needed to protect them from anchors or dropped objects or any sort of objects that may collide with the heads. So we utilized these steel protection frames, which were embedded within the scour rock for stability. Each of these steel protection frames weigh about 2 tons, and those were used to protect the risers from any sort of damage. So that comes to the end of my section. I'll let Casper take over and talk about the construction methodology.
Thank you, Daniel. As mentioned, I'm Casper Jansen and I work for Van Noord as Subsea engineer. And for this project, I was mainly involved as installation and project engineer. At the moment, located for another installation project in Australia. So Daniel will be sharing the presentation for me. I think we can start with the first slide of the installation works. For Van Noord, the project mainly consisted out of 3 phases: the trenching works, pipe preparation, and pipe installation. On this picture, you can actually see the pipes being prepared and brought into position for connection. That is a later stage. So we start with the beginning, which is, I think, an overview on the next page. We had, can you go to the next page, please? We had the outfall consisting of trench, dredging, and backfilling with the backhoe dredger, collar installation, pipe transportation and jointing, the pipe laying itself. After that, the diffuser installation, a protection frame installation, and then the canal, and finally rock installation. Our main challenges in this project were quite short preparation time and a small amount of space on site, which can actually be seen on the next slide, where we have an overview of the full site. Here you can see our backhoe dredger, and you can already see it's quite big for the area that we're in. And the nice thing of this project for me was that everything was very close, because you can see the red containers in the background. That was actually our site office. Then a bit to the left, you see the port and you see the pipe laying in the water with some collars. It's quite small, but you can just see it. And the trenching works were also just near the offices. So everything was pretty close by, but also meant you didn't have a lot of space, as you can see in this picture. At first, we started with the trenching works. In the next slides, you can see the overview of the trench that we made. So you can see here that the deeper blue part is actually the trench, and on the north side we dumped all the material temporarily so that it could later backfill with the material used or dredged used for backfilling. On the next slide we can see the backhoe dredger actually dredging, or the design that we made for how close the backhoe could come to the revetment, so that we could do most of the work with our biggest equipment. And on the slide after this, you can actually see the picture of how close we could come with our equipment. So what's nice to see here is that you see that the bucket of the dredger comes all the way to the trench box, which was used for the final stretch of pipe before the land started, because on the left side of this picture, about 5 meters, there was immediately a building being built. So we didn't have too much space as well for the trench itself. And if we go on, we can see another picture, but then made from the offshore side. So here you see that just after that winch that you see onshore, you see a crane working, which is installing the foundation for the building already. So again, we had to design this quite in a quite small area, but it all worked out, and yeah, it's quite nice. So after the trenching, or actually during the trenching, the pipe arrived, of which you have a picture in the next slide. And as you can see here, that's actually a short video, the pipes are brought into long lengths. So the pipes itself are approximately 300 meters in length, and they were towed all the way from Norway to Ireland. And even though we have only small waves here, towing these long pipes into a small port was quite difficult. But in the end we managed, and I think we have a nice picture of that in the next slide, the top view, where you can see that the one tug is towing the pipes inside, while the other tug is guiding it to avoid touching any of the key walls, because we had to cross a small corner. Okay, and I think if we go to the next slide, we can see actually the start of the collaring. So since this is a plastic pipe, we have to add concrete weight to get it to sink, of course. And if we start on the picture on the left, you can see a frame that we manufactured in order to lift collars onto the pipe with the bottom first, and then connecting the top as well. So in the middle picture, you see then the full frame lifting the collar onto the water. And on the right picture, you can see that we hooked the bottom of the collar underneath the pipe, after which we could lower the top part of the collar onto the pipe, which is shown in the next slide. Here you see that we lower it down, then we connect some bolts and nuts, and afterwards we can just let the pipe drop into the water again and remove the frame. And then for every 3.5 meters, we install the collar to add sufficient weight coating. So in order to do this, we have to do some checks, and that is what we call the installation engineering. And for that, we have a slide showing how we deal with this. Because we have to do some lifting, and all these plastic pipes can of course not bend too much, because at a certain point they will break. We check before we do any lifting operation, we check the bending of the actual pipe. And you can see the exact curvature of the pipe itself. Of course, it has to stay within certain limits. And that also has to do with the next part of our installation, which is the welding of the risers. So here we can see one of the risers. So as Daniel already mentioned, we had a couple of risers on this project, and they needed to be installed on site, which means that you have to make some holes in your pipe, which is obviously not very ideal for the strength. So what we did, we butt welded these risers onto the pipe, and then we had to lower it into the water again, which you can see in the next slide again. I think what's interesting to note here is that you can see that we use a spreader beam for the lifting. So contrary to when we were installing the collars, where you just have one lifting point, here we specifically choose to have 2 lifting points in order to keep the pipe straight in the middle and minimize the bending as much as possible, since we create this weak point. And then again, we do a quick calculation for this, what can be seen in the next slide. And if you compare this to the one where we did the collar installation, then you can see that it's a much lower bending radius. And on top of that, we then also install some bend restrictors, so that this weak point in the pipe will not be damaged during any sinking operations. So then the next part brings us to connecting all the pipes together before we can sink the pipe, which can be seen in this picture. Again, a pretty small port, but we were able to use the keyhole to lay it next to it, and you see the cranes a bit further down. If you can, you have to look properly. And there we then make the connection using 2 cranes for the installation. And at a certain point, you have a very long pipe, about 900 meters, which we can see in the next slide. Here are 3 sections together. If we go further on, here we can see the full pipe all connected, waiting to be towed into the installation point actually. And as you can see, this is already a very long pipe, and this is also for us the maximum we would like to install in one go. And for this we need very nice weather, as less waves as possible, and still it's not too easy, which we can see a couple slides later. So to install this pipe, we will use the float and sink method. I think most of you probably know the float and sink method, but just to be sure, since it's a plastic pipe, it is floating on the water, so we add concrete weight coating, but we don't add so much concrete weight that it sinks immediately. So that means that once we bring it into position and we fill it with water, the pipe will sink in this sort of S curve that you see here. In this project, we sink the pipe from onshore to offshore, And we use a foam pick as interface so that you make sure that on the one side you have water and on the other side you have air. So then we have some nice schematics of the pipe installation itself. So what you see here is that we use one multicat and 2 tugboats and some smaller additional vessels. The tugboats and the multicat do the most of the work. So we see them bring them into the shore setup. I think we go to the next slide and you see it a bit closer. And we maneuver it properly towards the messenger wire. Because the tugboat is relatively deep, we can of course not bring it all the way in. So we have to connect the pipe to a messenger wire, after which we use the winch to pull in the pipe. If you go a bit further in the slide, you can see it actually connected. And then we can see that the multicat is moving the pipe toward an anchor point, in this case the backhoe dredger. And because of that, then we have 2 fixed points, one onshore and one offshore. And then you see the pipe laying straight before we can commence with the sinking operation. So if we then look at the onshore connection point, that can be seen in the next slide, yes. Here we can see that you have some hoses connected, with those we will start pumping in the water. And we're actually just using seawater for this. And that means that we start sinking it from onshore. Here we already started, as you can see, because the pipe is already sinking if you look on the bottom of the picture. I think if you then go to the offshore end, here you see that the pipe is just floating without any water in it, and that there are hoses connected to the end of the pipe. Those hoses are used to let out the air, but also to blow in additional air if the pipe is slightly out of position. And then in the next slide, you can see how it looks if the pipe is slightly out of position. So this was during the sinking operation. We see here that one part of the pipe is already beneath the water surface, and that tugboats are actually keeping the pipe in position. But as we also see, between the 2 tugboats, the pipe is very straight, while on the bottom side of the picture, the pipe is in a curve. It is not ideal because we need the pipe to be in the trench. And this was happening due to quite a high current at that point. So what we did, we paused the operation for approximately 1.5 hours. And because we had this contingency and we could blow air again in another side of the pipe, we brought up approximately 20 meters, after which we could continue. So that mainly shows that you need to be able to be flexible in these kind of operations. And then again, I want to show you kind of the installation engineering part of it. Before we start, we actually look at the forces on these 2 tugboats. So we want to know if these tugboats are strong enough and if the pipe is strong enough not to bend around these tugboats while performing the sinking operation. There's quite some preparation involved to make sure that nothing goes wrong, of course. But in the end, everything went quite well, and we were able to install the pipe approximately within 0.5 meter distance from the center line. I think in the next picture, you can see the final part of this installation. But here you can see actually you can see 3 things. You see the survey vessel. That's the vessel on the right. You see it sailing over the pipe. This is a continuous process to make sure that during the pipe installation, we know exactly where it is. And then you see the pipe going down with the air hoses on top of it. And I don't know if it's visible for you, but there's also a cable connected from there to the barge. The last part of the pipe will be slowly sank into the seabed by letting out that wire. And then we finished the pipe installation. After that, we did some additional works underneath the surface for the diffuser installation, for instance, and the frames that were also mentioned earlier. But since it's under the water surface, we don't really have that much nice material of it, and it was kind of repetitive work. So I just want to focus mainly on the installation part. And then I think if the video works, Daniel, we can You can shortly show that. It is a nice overview of the installation a day, basically, because the full pipe was sank in 1 day. So Wallenberg, our client, made this video, and as you can see, we started quite early in the morning because we wanted to bring in the pipe at high tide. So we started as soon as it was light by connecting all the vessels and moving the pipe from its anchorage position into the trench box. So here you can see that the backhoe dredger is waiting to receive the end of the pipe. You can nicely see the site as well, all the cranes still there, people waiting to the pipe arrival. This is the pulling in of the pipe. This is actually the sinking of the pipe, so you can see that it goes relatively quickly. As long as you have the pipe in a straight line, you can also keep sinking it quickly. So it's mainly, you see in the background, you see the breakwater. When we were crossing sort of the point of the breakwater, then we encountered current where we had to pay more attention and move the tugboats closer together in order to keep the pipe in a straight line. And here you can see what happens if you don't use tugboats. You have a pretty big curvature, which is of course not really an issue because we're not sinking this part of the pipe. So this then went on for approximately, I think, half of the day after we did the commissioning of the pipe the same day still to be sure that there were no leaks. And after the pipe installation, then of course we went on with all the other smaller works, backfilling, and at the end, scour protection installation. I think that was mainly what I want to show in the slides of this project. So I hope you enjoyed it. And if you have any questions, please let us know.
Okay, you guys, that's the last slide, was it?
Yeah, that was the
Yes.
last slide. Yeah.
Right, okay, hang on a second. Okay, so if anybody has any questions, please put them in the chat. We don't do them as an open mic, but we have got some that have come in, so I will read them out and then either Daniel or Casper can answer them. So you should see them in the chat anyway. So a question for Daniel was around the pipe roughness for the hydraulics, the range chosen. Why was that range chosen, as 1.5 mil is sometimes used for gravity pipelines? So Daniel.
So is that question regarding the KS of the pipe?
Yes.
Yeah, so typically we use a KS of 1 mil just to account for any sort of future debris or roughness in the pipe. It's to the hydraulics. When you have a brand new pipe, it has much lower KS value. However, over time, over a period of say 20 years, you will have that KS go up. And so to be conservative, we start off by using a 1 mil roughness for the pipeline design. It's just for conservativeness.
I think it's about that value was agreed with the client with regards to what specifically was what was required. Any chance, is that your screen, Daniel? Can you remove?
Oh, sorry. Yeah.
Okay, next question is, how did you verify the integrity of the pipe after transportation? So this is for Casper.
Yeah, and I see that the next question is the integrity of the pipe after installation.
Yeah, you can do both if you want.
So yeah, I think so. Basically, integrity of the pipe means, of course, there are no leaks. And after transportation, the pipe was still floating high on the water. So you can be quite sure that there are no leaks in there. But after the installation, we did a proper test. So we did a leak test. We pumped in a certain pressure of water. I think it was a couple of bars. And then we waited for approximately half an hour to see what happened. And then if the pressure doesn't drop too much, your pipe is fine. And actually for HDPE pipes, the pressure can drop quite a bit because it's a sort of flexible material. So you do have a little bit of pressure drop, but of course, not too much.
Yeah, I'd probably just add to that as well. When you put the collars on, you usually pressurize the pipe slightly with air as well anyway, don't you? So you would know whether there's any problem in the pipe when you're fitting the collars on, because you slightly overpressure the air in there anyway, don't you?
Well, we at least didn't check it during the collar installation.
Yeah. Okay. So the next question was again to Casper. Why did you choose to side dump the excavated material to the north of a trench? Was there a risk that the currents would result in it basically going back into the trench? And the second question from Phil is also around how did you ensure the diffuser tees were vertical after installation?
So the first question about the currents, actually we had a cable laying at the south side, so we wanted to keep clear of that because we are of course not allowed to excavate material afterwards. So better to place all the material on one side. And indeed there was a slight risk of the currents moving it back into the trench. But since we had the backhoe dredger available during the whole operation, we could also do maintenance. And basically directly after the trench was finished, install the pipeline. And then of course, if there's only 1 or 2 days, that risk is not too high. And secondly, for the diffusers, indeed, it would be slightly difficult to do that. But we had at the end of the pipe, the connection was sort of on the top, so that at least we knew that the pipe when sinking was hanging on this one point. And also the collars are heavier on the bottom. So you assume that it goes straight down, and then afterwards we can check using the survey vessel with the multi-beam if they are indeed straight. And there's a little bit of a tolerance on it as well, so they don't have to be fully straight, but within a couple of degrees.
Okay, next question. What corrosion protection was used for the bolts on the weights? Don't know, Dan, when you want to answer what type of bolts were proposed and used on the collars?
Bolts on the collars, I'm gonna have to
I think Init Haskoning asked us to use I think it's called super duplex steel 1.442 or something. So
yes.
It was quite a nice quality steel, which we used for all the exposed steel parts.
So it was a grade 1.4462 from BSEN 188. And I think that was also part of the client's requirements as well. So the client specifically required that grade of stainless steel.
Next question was, what was the overall program duration for the Outfall works? And could you give a ballpark cost for this element of the project? I suspect probably we can't give a ballpark cost for the project, but construction duration, Casper?
So we started in April with mobilizing on site, so our equipment and our personnel, and we finished in July. So that is 4 months.
Did we have a total capital cost for the project? Did we have to include that, Daniel, in the project in the award summary? Can you cross check? Because there's a second question about that as well. I'll carry on with the other questions. Was there a visual inspection, divers or ROV as part of the sinking to ensure the pipe was in the trench, or was it all monitored, confirmed from surface stroke surveys?
So the sinking of the pipe itself was all monitored from the surface, which is of course much safer, but it's also much more detailed because with survey equipment, we can see a point every millimeter if we want to. So it's very, very clear. And we usually prevent diving as much as possible, but we did use divers for the installation of the riser. So in that sense, they made pictures to show that everything was nicely installed, which was also a confirmation that it was in the right location.
Did you find it cost, Daniel?
Yeah, we didn't put a cost into that into the information. I think we said that was going to be confidential.
Sometimes we don't have visibility of what the overall total capital project costs is from the client. You know, so it is quite difficult sometimes for us to be able to confirm that. Another question on hydraulics, Daniel, about the KS. Did you not use a higher KS for getting towards end of life? And you assume you took into account the salinity of the water. I'll let you answer that, Daniel, but I think some of that's not really applicable, is it?
Yeah, so we don't take into end of life. So essentially, when we choose the KS value of 1, we've already accounted for the design life. So on this job, it was a 50-year design life. So that 1 mil, we assumed or that was sufficient KS value for the lifetime of the outfall. In terms of the other questions, I think that's the salinity is not really applicable. The KS value is more for debris or any sort of leftover unwanted contaminants in the pipe.
Yeah, the water discharge is a wastewater, so there's no saline water internally, so the risk of marine growth is a lot lower, isn't it?
Yeah.
Okay, we've had another question around the capital costs, which I think I've covered really, that we don't actually have full visibility of what the total project cost was. Was the PE pipe sourced and transported from Norway was one of the questions.
Basically, you can either choose between long lengths or sections of 12 meter. And logistically, getting it from Norway is quite easy because you have these long lengths, so you don't need equipment to weld these pipes together in the port. And of course, since it was already quite a small port, we didn't really have room for that. So in this project, I think it was the most logical option. Yeah.
Okay, there's still quite a few more questions. Can I ask, because we are on a time limit with these webinars, that we just quickly go through the remaining ones that are posted and nobody posts anymore, please, because we've done 45 minutes now. So we'll just try and run through these very quickly if we can. Considering the reach of the excavator arm, is there a maximum depth that you can use the installation technique limited to?
I would say the maximum dredging depth in this case, but you can of course also use a bigger piece of equipment. So then you can increase it. And you will get some technical limitations, but you can go much deeper than what we did here, which was about 16, 17 meters, I think.
How important was it to be able to use the river channel for assembly of the pipe once delivered? Presumably, it is still possible to do this along the shore if a river channel is not nearby.
Well, along the shore is possible, but this was in the Irish Sea, so I wouldn't recommend it. And also, you need quite big equipment to keep your pipe in place the whole time. So it would get at least much more expensive and less safe. So we definitely prefer to do it in a sheltered area.
Any issues with the trenching filling before pipe installation? And how did Van Oord know the pipe had been laid to the correct levels?
Infill was not really an issue, especially since we had the backhoe there to do maintenance. And the correct level, we basically have a design left from Haskoning, which we then put into our equipment. And then in our survey equipment, we can see if the pipe is on the correct level.
There was a mention of maximum length of the pipeline the Van Oord were comfortable installing, which was around 900 meters a kilometer. Presumably, if the length is longer to lay, you need to do the installation in sections.
Yeah, indeed. So what you would do in that case, you take a shorter length, let's say 500-600 meters, and then you use the flanged connections and connect them on the water. So in this case, we were more comfortable in doing the connection with the cranes from shore, but you can of course always create a sort of offshore lifting barge where you lift 2 pieces on top, make connection and lift into the water. Well, a big part of the pipe is already on the seabed, so that you limit the amount of floating pipe.
Yeah, next one. What was the water depth at the outfall endpoint and what type of diving operations were required?
So the diving operations were mainly connecting the risers to the pipe, and that consisted of sort of maneuvering them in place and connecting the bolts and nuts. I think the depth was approximately 16, 17 meters at the bottom of the trench. That are the main diving operations. We did, for instance, also need to disconnect the hoses and some small work, but nothing much besides connecting these small items.
Hydraulics. Another hydraulics question is about discharging a wastewater into saline water. Obviously, there's a difference in density that should be taken into account during the hydraulic design. Daniel, I think you can respond and confirm that we did that.
Yeah, we did do that. I think we allowed, from memory, we allowed an additional head loss in the results to allow for the difference in densities between the effluent discharge and the receiving seawater. I think that was done in line with the WRC design guide for marine treatment schemes. So yeah, that was included in the hydraulics.
Yeah, there's a density adjustment as part of the hydraulics calculation, so so it is accounted for as part of the calculations. There's another question in there about the bolt and steel specification. I'm not going to answer that here in the chat. We're not going to post that, but I would say that if there are specific questions like that that are that those should be raised, can be raised direct through to the panel, to the guild panel, because there's quite specific technical requests, and I prefer not to put that in the chat. So thank you very much, everybody. We're 50 minutes. This was excellent. We had over 109 people in the chat, in the presentation, which was certainly one of the highest numbers I've been with. Well done. Thank you, Daniel and Casper. This will be recorded, obviously, and added onto the Guild YouTube page. And I'd just like to say as well, on behalf of the Guild, if you have a look on our events page, you will see what's coming up. We have another webinar on intakes and outfalls on the 14th of May. That is 2 international projects in Mexico and Argentina, which have used large diameter steel pipes. So those are quite interesting. And the other one is to be aware of our 12th annual conference, which is taking place on May the 23rd. So if you'd like to go, it's about hydrogen, all sectors all together. So again, if you go onto the Guild website, you'll be able to see more details and register for that. So thank you very much to everybody. Thank you for attending, and I hope forward to seeing you again in the future. Thank you very much.